Okay, so now we're going to introduce this concept of backward error analysis, which is a really useful concept in the analysis of geometric numerical integrators. So let me first try to contrast forward versus backward error analysis. Okay. So let's say that you have a sufficiently smooth differential equation. So consider the discretization of a sufficiently smooth differential equation. Okay, let's say just dz dt equals to f of z, and I'm going to discretize this by some one-step method. Okay, so zn plus 1 is equal to psi h applied to zn. Okay, and let's say it has order p greater than or equal 1. Okay, which implies that there exists a constant, so let's call it m, greater than 0, such that if you look at the operator norm, if you will, the induced operator norm of the numerical one-step method, right, psi h applied to z minus phi h applied to z. Well, it's not really the operator norm, so this is just actually applied to a certain initial data. Okay, so then this is less than or equal to m h to the p plus 1, right, for some appropriate subset of phase space and for h sufficiently small. Okay. So this is really just sort of the usual notion of forward error analysis so far. Okay. Then if you have, it's like a local error estimate like this, then you can basically use sort of the Gronwall, it's like lemma, to conclude the following. So this, you can recall that this typically implies that that if you look at z at tn minus zn, right? So the exact solution versus the numerical solution, this is less than or equal to some constant kappa times e to the tn times l minus 1 h to the p. Okay, for some l greater than 0, which is usually related to, in some way, shape, or form, it's like to the Lipschitz constant of f. Okay. Okay, and you have a constant kappa, which is greater than 0 and independent of the time tn and the step size h. Okay, all right. So the problem, of course, with this kind of global error estimate is that you know, it's like the bound diverges exponentially. It's like as time increases. So it's not particularly useful when basically Tn times L is much larger than 1, unless you take extraordinarily small time steps. Okay, so so let me just state that. Just erase this part here for now. Okay, so this estimate becomes useless whenever basically Tn times L is very large, unless very small time steps are taken, right? Okay, all right. So, so in particular, this is not satisfied when sort of low order methods are used. To simulate sort of large nonlinear systems. Over very long times. Okay, so so you can ask, it's like, well, what can you do instead? And again, it's like this leads to the concept of what is called backward error analysis. So so let me say a little bit about that now. Okay, so this is sort of the, again, the traditional forward error analysis result. You look at a continuous dynamical system, you look at its discretization, and you ask how close the discretization is to the exact solution of the original continuous dynamical system. Okay, so that's the traditional forward error analysis result. And we'll see in a little bit that backward error analysis sort of turns this on its head. So what do I mean by that? So what is backward error analysis? So backward error, or sometimes referred to as all modified equations. Okay, is concerned with the following. You're concerned with finding a modified equation, right? Let's say dz dt is equal to f tilde, okay, z. And then now this modified equation is going to typically be an asymptotic series in h. Okay, so there's a h dependence now. Okay, so you have this modified equation which depends on the step size h. Okay, such that your original one-step method, psi of h, is a more accurate solution to this modified differential equation. So it's a more accurate solution or approximation of the exact flow map of the modified vector field, okay, than the original vector field. Okay, all right. So so that's sort of the idea, is that you, for example, you know, we have a one-step method. It's like, which is an order p accurate approximation of the exact flow of the differential equation dz dt is equal to f of z, all right? And I want to find an f tilde, which now depends on h, such that the one-step method is a higher order accurate approximation of this solution or this sort of flow map than to this flow map, okay? All right, so so perhaps it's helpful to look at an example of this just to illustrate the idea. Okay, all right. All right, so let's consider explicit Euler. Right, which says that Zn plus 1 is equal to Zn plus h times f of Zn. So you can ask, well, okay, so you know, of course, explicit Euler is a first order accurate approximation of, you know, it's like the flow map. You cannot accurate approximation of some other, of the flow map associated with some other vector field. Okay, so let's consider the Taylor expansion. Of the flow map, right? Okay, so this is z at tn plus 1 is equal to zn plus h f at zn, right, plus h squared over 2 f prime at zn f at zn plus something which is big O of h cubed, okay? Right, where of course f prime of z is the Jacobian. Of f at z. Okay, so this is of course just the usual Taylor expansion. All right. So what you want to do then is you want to think of this as we want to modify the vector field basically. All right. So how do you do this? Okay, so you take the difference of the numerical method, right, the Euler method, applied to the initial data and the flow map, okay? And what you get is the following. So of course you know that the truncation error is of order h squared, which is why the forward Euler method is first order accurate, right? So the leading order truncation term is exactly this, plus something of order h cubed, all right? So I mean the intuition, if you will, is that you somehow want to put this term in some way, it's like and you want to use it to modify the vector field, okay? All right, so let's consider the following modified equation. Okay, and I'm going to label it by star, and let's look at dz dt is equal to f tilde 1, okay, of z, and it depends on h now. Okay, and I'm going to write this as f of z minus h over 2, f prime at z, and f at z. Okay, and then as you might expect, what is going to happen is that the index is going to allow you to sort of construct higher and higher order corrections. It's like of the vector field such that the Euler method is a more and more accurate approximation of some flow map, okay, for a modified vector field. Okay, and so this has an associated flow map. Right, which is f tilde 1 h, phi f tilde 1 h, and you can check that the exact flow map of this equation, right, looks like the following. Well, it's approximately equal to. Okay, so it's going to be Zn plus h f1 tilde of Zn h plus h squared over 2 f tilde 1 prime Zn h f tilde 1 Zn h. Right, so this is of course just the quadratic approximation, or we're only taking quadratic terms. It's like of the Taylor expansion for the solution of this modified equation. Right, it's exactly the same as we had done before. Okay, and then you know what f1 is. It's f1 tilde is in terms of the f's. So I substitute it into these expressions, and then I again sort of truncate. It's like so I ignore terms which are cubic in h, and then this is approximately equal to z n plus h f of Cn minus h over 2 f prime Cn f Cn plus h squared over 2 f prime Cn f of Cn. Okay, all right. So, and of course, what happens now is that if you look at the terms in h squared, it's like this. This factor h multiplies into this. You get h minus h squared over 2 f prime Zn f Zn term, which cancels out this h squared over 2 f prime Zn f Zn term. So this term cancels with this, and you're just left with Zn plus h f of Zn, plus an error term which is of order h cubed. Okay, so this tells you that the sort of the Euler method, right, applied to the vector field that's like f, right, is a better approximation of this modified vector field f tilde 1, right, because now the error is of order h cubed, the local error is of order h cubed, which means that the Euler method is a second order accurate approximation of this modified vector field. Okay, so this implies that Euler is a second order accurate approximation of this modified vector field. Okay, so why is this sometimes a useful thing to do? It's sometimes a useful thing to do because when you look at these modified equations, sometimes you're able to extract useful sort of analytical information about the solution behavior. Okay, and so what that sort of tells you then is that it tells you, for example, that when the Euler method is applied, it's like to it's like to a dynamical system, it behaves a little bit more like this modified equation than it does the original equation. And that gives you an idea of the errors. It's like you introduce, it's like when you use that discretization to discretize your original dynamical system. Okay, and of course, as you might expect, you can actually extend this further to higher order, right? So this notation f tilde 1 is suggestive that I've only essentially looked at a some asymptotic series. It's like corresponding to the modified equation, but I've only taken it up to first order in h. So let's see what happens if you keep doing this. Okay. All right. So the idea, of course, is that this can be continued, right? So this can be continued. So you consider for the modified vector field, which looks like the following. So the I z h is f of z plus h delta f1 of z plus h squared delta f2 of z, and so on, right? Okay, and in our initial case, it's like we found that in our analysis, we found that delta f1, right, was equal to minus 1/2 f prime of z, f of z. Okay, and then in general you can compute it's like the higher order terms by looking at the Taylor expansion of the exact flow of the modified vector field, right? So can obtain delta fi of z by sort of computing the Taylor expansion. Of the exact flow of fi tilde of h, and choosing the modified equation such that we're out of space. So let me write down what it has to have. Okay. All right. So what you want, of course, is that you want the exact flow of the ith modified ith term, if you will, or the ith truncation. It's like of the modified vector field when applied to Zn. This is specifically, of course, for the Euler method, right? So you want that this is equal to the exact, to the one-step method, the Euler method applied to Zn plus an error term which looks like big O of h to the I plus 2. Okay, so in particular, then for forward Euler, this looks like Zn plus h f Zn plus big O of h to the I plus 2. So that's something you can do basically term by term in order to solve for all these delta fi's. Okay. So then what happens is that the forward Euler method can be viewed as a method of order I plus 1, right, for the modified equation dz dt is equal to f tilde I of ch. Okay, so what sometimes happens, not always the case, what sometimes happens is that you can do this expansion term by term. It's like all the way up to an infinite number of terms. So, and then there's some sort of limiting modified equation. It's like which is in some sense the exact solution. Oh, sorry, let me rephrase that. So there's, if you could, it's like do this expansion, it's like, and it yields a convergent series, then you will have a modified vector field whose exact flow is basically equivalent, it's like to the Euler method, okay? So if we assume that we can increase I to infinity, right? And this limit, so I goes to infinity of f tilde I of ch is well defined. None of these are necessarily true, right? But if you could have that, then we may take sort of this limit f tilde ch is the limit as I tends to infinity of f tilde I ch, right? And the Euler method is the exact solution just erase this. Of this modified differential equation, dz dt is equal to f tilde ch, which also means that the numerical one-step method is equal to the time h of this modified vector field. Okay? All right, so that would be what happens in an ideal situation. In practice, you oftentimes find that the series diverges. Okay, you get, instead of a well-defined series, you get what is called an asymptotic series, and then you have to truncate the asymptotic series. It's like in a good way, assuming certain sort of analyticity or regularity properties. It's like of the vector field, and then you don't have this exact correspondence, and that's really just part of life, because in some sense, you can check that not every single map can be approximated, or let me rephrase that, not every single map is the time h flow of a vector field. Okay, and as a consequence, there is a gap between time h flows of vector fields and maps like this. So you don't expect necessarily that all of these asymptotic series will converge. Okay, so now let me briefly say something about what happens if instead of the Ford-Euler method, you have a general p-Forder accurate one-step method. Okay, so now let's consider the case of a sort of one-step method with order p, again greater than or equal to 1. Okay. So ideally, of course, what you would like to find, right, a modified differential equation such that the following is true. Right, the first thing is that the modified vector field f tilde of h, right, is close to the given vector field. Just to say that in some appropriate norm, f of z and f tilde of ch, right, is some big O of h to the p. And the other thing you would like is that the numerical computed solutions can be considered as the exact solutions of the modified vector field. Which basically means that right, the numerical method applied to Z is equal to the exact flow map of the modified vector field with step size h applied to Z. Okay, so basically, if these two can be achieved, so let's suppose that sort of 1 and 2 can be achieved. right? Then we can compare the exact flow map of the modified vector field with the flow map of the original vector field, right? So in general, you don't necessarily gain much, right? Solutions of the two differential equations will diverge. Sort of exponentially fast. But it becomes useful, but backward error analysis becomes useful if you can show sort of both types of solutions, both the original differential equation and the solutions of the modified equations have similar qualitative properties, right? Okay, so the hope, if you will, is that if you had a nice method, right, then you can show that it's like the flow of the modified equation has similar qualitative properties to the flow of the original differential equation, and that is sometimes useful because it's oftentimes difficult to establish those things by other means. Okay, so let me just stop here.